Hello everyone. I wanted to do this video as a follow-up to the one I made about rogue planets to cover some points I didn't adequately address. One commonly cited claim in the field of astrobiology is that a rogue planet with a thick hydrogen-rich atmosphere could possibly host liquid water on its surface. The argument goes that hydrogen is a potent greenhouse gas and can thus trap heat. This is true, but not in the conventional sense. Most greenhouse gases have large absorbance bands in the infrared range, and thus trap energy emitted by the surface in the form of infrared radiation, which comprises the majority of a planet's blackbody emissions. Hydrogen has very low absorbance in the infrared range, but it can retain heat another way. As you go higher in the atmosphere, the temperature drops. This is because as a parcel of air in the atmosphere rises, the pressure decreases, and, in accordance with the ideal gas law, the volume increases and the temperature decreases. The opposite happens when a parcel of air sinks. This results in what's known as the adiabatic lapse rate, or the rate at which the temperature drops the higher you go. This is equal to the surface gravity divided by the specific heat of the atmosphere. Now obviously, the temperature can't keep decreasing indefinitely, or you will go below absolute zero. Rather, it ends as you reach a pressure of roughly 0.1 atmospheres. On a rogue planet, the temperature at the altitude which has this pressure would likely be the equilibrium temperature. This is the temperature where the blackbody emission of an object is the same as the heat energy it receives. On a rogue planet, all of this would come from beneath, largely driven by the decay of radioactive elements deep below the crust. The rate at which energy is input to the surface of the Earth from below, or the geothermal flux, is on average 87 milliwatts per square meter. This gives an equilibrium temperature of 35 degrees Kelvin. So, how thick would the atmosphere have to be to support liquids on the planet's surface? The average specific heat of hydrogen between 273 degrees Kelvin, the melting point of water, and 35 degrees is about 13 kilojoules per kilogram degree Kelvin, giving an adiabatic lapse rate of 0.7538 degrees per kilometer. This means the altitude where the pressure is 0.1 atmospheres and the temperature is 35 degrees Kelvin would have to be greater than 317 kilometers above the surface. In order to get to 373 degrees Kelvin, the upper limit for most life, this pressure would have to exist 450 kilometers above the surface. How much hydrogen would be needed to produce such an atmosphere? The change in atmospheric pressure with altitude is determined by the following equation, where P0 is the surface pressure and h is the scale height. The scale height is the product of the gas constant r and the temperature divided by the product of the average molecular weight of the atmosphere and the acceleration due to gravity. Since we're looking at a wide range of temperatures, we can modify the equation. Instead of h, we can find the theoretical scale height at absolute zero, or h0, and multiply it by the temperature at altitude, which we already calculated. With hydrogen gas having a molecular weight of 2, we get a h0 of 0.4242. Plug this into our equation, and we find the minimum surface pressure an Earth-like rogue planet would need to support liquid water on the surface is 1.53 atmospheres. Conversely, if the surface pressure was 1.7 atmospheres, the temperature would exceed 373 degrees Kelvin. So, we can say it's at least theoretically possible for a rogue planet to host liquid water on its surface. Such a world would likely have water ice clouds in its lower atmosphere, with methane clouds in the upper atmosphere. But being able to exist in theory and in reality are two separate things. The primordial atmosphere of the Earth is believed to have had a partial pressure of hydrogen between 0.1 and 0.3 atmospheres, well below what is needed to have liquid water on the surface if it was a rogue planet. But all of these calculations pertain to an Earth-sized planet. A larger planet would be able to collect and keep more hydrogen from the surrounding space due to its deeper gravity well. In fact, the ice giants in our solar system, Uranus and Neptune, have a thick hydrogen-helium atmosphere overlying a mantle made of water and ammonia. Their atmospheres are so thick that they comprise over 10% of the planetary radii, and at the bottom, the pressures and temperatures are so high that the water is in a supercritical state. This in spite of the fact that they only get a fraction of the sunlight Earth does. So, it stands to reason that at some point between the sizes of the Earth and Neptune, the planet could collect and retain enough hydrogen during formation to hold an atmosphere thick enough to support liquid water on the surface. One thing to note is that not all of the molecular hydrogen that existed on the early Earth was necessarily blown off into space. It could have reacted with other chemicals in the atmosphere. Earth and Venus have large amounts of carbon dioxide and carbonates, and in the high temperatures present during planetary formation, these would react with hydrogen to form methane. For some perspective, Earth currently has enough carbonates in its crust to increase the atmospheric mass 100-fold if they were in their gaseous CO2 form, as is the case with Venus. On top of that, a super-Earth would accumulate more oxygen and nitrogen-based compounds, which would react with the hydrogen to form water and ammonia. Although, as the planet got larger, the ratio of hydrogen to heavier elements would increase until all the others were in their reduced form, allowing molecular hydrogen to build up. But by the time you reach this point, the pressure at the bottom of the atmosphere may very well exceed 150 megapascals, the theoretical limit microbes can grow under. Now, there are some ways it could possibly get hydrogen. For one, it could fly through a molecular interstellar cloud and get hydrogen from it. However, objects in space are moving fast, with many interstellar bodies traveling at velocities of around 23 kilometers per second relative to one another. This is over twice the escape velocity of the Earth, and the frictional heating caused by the planet moving through such a cloud would heat up the upper atmosphere, accelerating the rate at which hydrogen molecules fly away and potentially causing the planet to lose more hydrogen than it gains. So yeah, a way to get this much hydrogen on a rogue planet is far from guaranteed. I also talked about the possibility of life surviving deep underground if an Earth-like rogue planet had no atmosphere. To recap, I used the current geothermal gradient, or the rate at which the temperature increases as you go deeper into the Earth, of the continental crust of 27.5 degrees per kilometer. On the continental crust, the geothermal flux is 65 milliwatts per square meter, which gives an equilibrium temperature of 32 degrees Kelvin. So, if we crunch the numbers, we get that we'd have to go 8,764 meters down to reach temperatures in excess of 273 degrees Kelvin. Since continental crust has an average density of 2,700 kilograms per cubic meter, the pressure at that depth would be 232 megapascals. The theoretical pressure limit microbes can grow at is 150 megapascals, seemingly rendering the deep crust uninhabitable. However, the geothermal gradient would be different if the Earth was a rogue planet. On the modern Earth, the geothermal gradient is affected by heat coming from below and from above as the sun warms the surface. For a rogue planet, this wouldn't be the case, making the calculations easier. If you have a source of heat energy at one end of a stretch of material, i.e. the crust, the heat flow will be equal to -1 multiplied by the thermal conductivity, K, divided by the heat gradient. The average thermal conductivity of the continental crust is 2 watts per meter Kelvin. Dividing the continental geothermal flux by this gives a steeper geothermal gradient of 32.5 degrees per kilometer. With this geothermal gradient, we'd have to go 7.42 kilometers deep, where the pressure would be 196 megapascals to reach 273 degrees Kelvin. This is again above the 150 megapascal limit, but it's important to remember that this gradient isn't uniform. In some places such as continental hotspots, i.e. Yellowstone, the geothermal gradient will be much steeper, and you could get temperatures above freezing at depths shallow enough that life could survive. While it's tempting to use modern microbes inhabiting the deep crust as an analog, there are some stark contrasts. For one, at deeper depths, the porosity will be lower, so there will be fewer microhabitats, and there won't be any oxygen, both making survival more difficult for any microbes clinging on. But continental crust only covers a fraction of the Earth's surface, with the majority covered by oceanic crust. Here, the geothermal flux is greater, being 100 milliwatts per square meter. Also, it's covered in water. Although this will certainly freeze if Earth becomes a rogue planet, water ice has a comparable thermal conductivity with a much lower density than Earth's crust, facilitating higher temperatures at lower pressures. The equilibrium temperature over the oceanic crust will be 36 degrees Kelvin. The thermal conductivity of ice changes with temperature, but for the sake of easy calculations, we can make it 3 watts per meter Kelvin. This results in a heat gradient through the frozen oceans of 33.3 degrees per kilometer. The average depth of the oceans is 3.69 kilometers, so at the top of the oceanic crust, the temperature will be 159 degrees Kelvin and the pressure will be 36 megapascals. The thermal conductivity of the oceanic crust is around 2.3 watts per meter Kelvin, which gives a geothermal gradient of 43.5 degrees per kilometer. Since the temperature has to rise 114 degrees for there to be liquid water, we'd have to go 2.62 kilometers into the oceanic crust to reach this point. With an average density of 3,000 kilograms per cubic meter, oceanic crust is slightly denser than continental crust. 2.62 kilometers into the crust, the weight of the overhead rocks will produce an additional pressure of 77 megapascals. Add this to the original 36 resulting from the weight of the ice and you get a pressure at depth of 113 megapascals, well below the theoretical pressure limit. How much further down the crust could life survive? At a depth of 3.88 kilometers, the pressure will reach 150 megapascals, and at this depth the temperature will be 328 degrees Kelvin, or 55 degrees Celsius. This is well below the temperature limit microbes can grow under, with one species being able to reproduce at temperatures in excess of 100 degrees Celsius. So, in this scenario, the pressure would be the limiting factor. Going back to the oceans themselves, using the calculated thermal gradient in the ice, at a depth of 7.12 kilometers, the temperature exceeds the melting point of water. There are a few parts of the ocean deeper than this, so there could still be pockets of liquid water persisting if the Earth became a rogue planet underneath the ice. In summary, if Earth became a rogue planet, life could still hang on in a few pockets of the deep continental crust and over most of the oceanic crust. But the geothermal gradient isn't constant and has been slowly decreasing since the Earth formed. As it gets smaller, the depth at which the temperature will exceed 273 degrees Kelvin will increase. At a geothermal flux of 82 milliwatts per square meter, the temperature at a depth of 3.88 kilometers below the ocean floor, the depth where the pressure reaches 150 megapascals, drops below 273 degrees Kelvin, rendering most of the oceanic crust uninhabitable. At this point, life can only cling on near oceanic hotspots or beneath the deepest parts of the ocean where the pressure at depth will be lower. While a planet could theoretically be flung out of its solar system at any time, if this is to happen, it's most likely to occur early on, within the first billion years of the solar system's formation. At this point, plate tectonics wouldn't have begun, and the crust would be undifferentiated, being mostly composed of the mafic oceanic crust. The average thickness of the crust would have been around 37 kilometers, and land would only exist in the form of a few small islands, i.e., an ocean would cover the planet. It would have an average depth of around 70% of the modern oceans, since 70% of the modern Earth is covered by oceans. So, let's say Earth was flung out in this phase. What would the deep crust be like? For one, the average geothermal flux would be 174 milliwatts per square meter, twice what it is now. At this flux, the equilibrium surface temperature will be around 42 degrees Kelvin, and the temperature gradient in the ice will be around 58 degrees per kilometer. So, beneath 2.58 kilometers of ice, the temperature and pressure will be 192 degrees Kelvin and 25 megapascals. The geothermal gradient through the crust would have been 75.7 degrees per kilometer, meaning you'd have to go 1.07 kilometers down to reach habitable temperatures. Here, the pressure will be 56 megapascals. When the temperature reaches 373 degrees Kelvin, the boiling point of water at 2.39 kilometers in the crust, the pressure will be 95 megapascals. So, in this scenario, temperature is the factor limiting how deep microbes can live, with anything being cooked before it gets crushed. With the crust and oceans on the primordial Earth, you'd hit a pressure of 150 megapascals at a depth of 4.25 kilometers into the crust underneath the ocean. As time passed, the geothermal flux would decrease, and at a flux of 123 milliwatts per square meter, the temperature at 4.25 kilometers deep will drop below 373 degrees Kelvin, making pressure the limiting factor determining how deep life can survive. With the current average geothermal flux of 87 milliwatts per square meter, the temperature at 4.25 kilometers drops below 273 degrees Kelvin. So, if in alternate prehistory scenario, the Earth was flung off into interstellar space 3.7 billion years ago, around the current time, much of the deep crust would have become uninhabitable, and the remaining life would have been confined to hot spots. Now, some of you will probably type in the comments that some organisms can grow at temperatures at 122 degrees Celsius, or 395 degrees Kelvin, or at temperatures below 0 Celsius. However, what we're finding is that what renders some environments uninhabitable is not a single variable, pH, temperature, salinity, etc., but combinations of these extremes. Since any microbe surviving deep down in a rogue planet will already have to be dealing with extreme pressures, I use the standard 0 to 100 degrees Celsius habitability range. But could any microbes clinging on get a second chance before fading into darkness, as even the crustal hotspots became too cool to support life? Perhaps if the planet could collect a lot of hydrogen when flying through a dense molecular cloud, warming the temperature sufficiently for liquid water to exist on the surface. If this happened, some volcanoes would release carbon dioxide into the atmosphere. Microbes known as methanogens can react carbon dioxide with hydrogen to form methane in water to power their metabolism. These would likely congregate in hydrothermal systems where large quantities of carbon dioxide are emitted by the vents. Here, they would grow into thick microbial mats. While productivity would decrease as you got further from such vents, the surrounding environment need not be sterile. Some microorganisms are known to power their metabolism by a process known as trace gas oxidation. Here, small amounts of methane, hydrogen, and carbon monoxide, which exist as minor constituents of the ambient atmosphere, are reacted with oxygen to produce energy. Similarly, methanogens could react small amounts of carbon dioxide which exist as a trace constituent of the ambient atmosphere with hydrogen to produce methane. Although, since the trace constituent, CO2, is the oxidant and the major constituent, hydrogen, is the reductant, what we'd have here is trace gas reduction. Oxidizing all of the reduced trace gases in Earth's atmosphere at sea level will give you 75 millijoules per liter. 1 mole of carbon dioxide reacting with hydrogen to produce methane will produce 131 kilojoules of energy. This means you'd have to react 573 nanomoles of carbon dioxide with hydrogen to get the same amount of energy as you'd get from oxidizing all of the trace gases in 1 liter of air. So, if we use the ideal gas law, we find that if the partial pressure of carbon dioxide on our hypothetical rogue planet was greater than 1.3 pascals, trace gas reducers could get more energy from the atmosphere than the trace gas oxidizers get here on Earth. For some perspective, the partial pressure of carbon dioxide on the pre-industrial Earth was about 28 pascals. So, even with atmospheric concentrations of carbon dioxide much lower than the modern Earth, such a world could support comparable productivity to the most desolate regions on the modern Earth, where trace gas oxidation dominates primary productivity. Apart from carbon dioxide, sulfite produced by reactions between sulfur dioxide in the magma and water would have been released by the vent. This can also be used as an electron acceptor to oxidize hydrogen and can even be used to oxidize methane. While reacting atmospheric hydrogen with carbon dioxide released by volcanoes would act as the main mechanism of primary productivity on our hypothetical rogue planet, there is a key difference between what we have on Earth and what would happen there. Photosynthesis sees the key reactants in metabolism recycled. But on the rogue planet, there would be no means to replace the hydrogen, causing the atmosphere to be drawn down over time. So how long would this take? Well, let's say that after flying through the cloud, the surface pressure was 1.6 atmospheres. This means 0.07 atmospheric masses of hydrogen could be consumed before there wasn't enough hydrogen for liquid water to exist on the surface. How long would it take to do this? Well, with carbon dioxide having an average molecular weight of around 44 grams per mole, and it taking 4 hydrogen molecules per methane produced, 11 kilograms of carbon dioxide would consume 2 grams of hydrogen. Roughly 300 megatons, or 3 times 10 to the 11th kilograms of carbon dioxide are released every year by volcanoes, which would consume 5.45 times 10 to the 10th kilos of molecular hydrogen. The mass of Earth's atmosphere is 5.15 times 10 to the 18th kilos, and 7% of this is 3.6 times 10 to the 17th kilograms. Divide this by 5.45 times 10 to the 10th kilos per year, and we get that after 6.6 million years, the amount of hydrogen would drop below the 1.53 atmosphere mark, making the temperature drop below freezing on the surface. At 1.7 atmospheres, the pressure that will cause the surface temperature to exceed 373 degrees Kelvin, it would take about 16 million years for the surface pressure to drop below 1.53 atmospheres. So, if such a world collected hydrogen which retained enough internal heat to allow life to live on the surface, it wouldn't last long in geologic timescales. Although, once the surface became too cold to be habitable, microorganisms could still continue to survive using hydrogen to reduce volcanic carbon dioxide deep underground. Now, if the planet had a lower geothermal flux than the Earth, it would need more hydrogen in the atmosphere to allow liquid water to exist on the surface. This also means the surface temperature would be between 273 and 373 degrees Kelvin over a wider range of pressures, i.e. a total mass of hydrogen in the atmosphere. So, if a planet had a lower geothermal flux, it could host a biosphere sustained by a CO2 reduction for a longer time. In summary, if a planet was flung out into interstellar space, it could potentially support hardy microbes deep below its surface, where the geothermal heating keeps the temperatures above freezing. But by around 4.5 billion years after the planet's formation, the depth where the temperature rises above freezing would host pressures too high for any organisms to grow and reproduce, confining any remaining life to volcanic hotspots. Life on the surface could get a second chance if the planet somehow collected enough hydrogen to form a thick atmosphere. However, if this happened, the surface would likely only be habitable for a few million years. Although, a question that comes up is what would happen if one of these rogue planets, with life clinging on deep below the surface, was captured by another star and settled into its habitable zone. I guess that's a topic for another video.